Okay, we'll be solving questions 11 to 20 in this video. And the question 11 says that we have 1 mole of a monoatomic ideal gas which goes through the process 1, 2, 3, 4 in this case, and we have to find out the net work done in this process. So the net work done, we'll just evaluate work in each of the 4 processes. If it had been a PV graph, it would have been easier to simply calculate area under the graph. But since it's a VT graph, we'll just have to do with calculation for each individual process. Now, the first process from 1 to 2 is an isothermal process that is taking place at 300 Kelvin, for which the initial and final volumes are also known. They are 10 and 20 liters. So for this, I can write work done as minus of nRT ln of V2 by V1. The values are known, so you can always calculate this work done. Let's call it W1. For the second process, so process 2, 3, we have V by T as a constant according to the graph. And for the ideal gas, V by T is nR by P. So as V by T is constant, it's because pressure is also a constant in this case. So it's an isobaric process, for which I'll write work done, let's call it W2, as minus of P delta V. And you can always write the pressure as nRT by V. And you can use any one of the states. You can either write as nRT2 by V2 or nRT3 by V3. Either way, you get the same value for pressure. Delta V can be written as final minus initial, which is V3 minus V2 in this case. The process 3-4 again is an isothermal process at 600 Kelvin, for which work done is minus of nRT. This T is 600 Kelvin. The work done is minus of nRT ln of V final by V initial. So it's V4 by V3 in this case. Let's call it W3. The last process is process 4 to 1, which is at a constant volume of 10 liters. It's an isochoric process, for which work done is simply 0. Now you can find out net work done in the cycle by adding up W1, W2, W3 and W4. The next question is question 12, which says we have insulating partition. We have insulated container of gas. So we have a container of gas in which you have a partition. Gas on the left has P1, V1 and T1 as the state variables, and on the right it has P2, V2 and T2. Now one of the equations which is normally used in such a case is that N1 plus N2 is N final. So you write N1 as P1, V1 by T1, N2 as P2, V2 by T2, and N final by P final, V final by RT final. So this equation, in this case, it will not work because the V final has to be V1 plus V2. So this is known according to known variables, but both P final and T final are unknowns in this case. So we cannot use this one equation to solve it. Rather, what we'll do is we'll write this. We'll write heat gained by gas in one chamber that is equal to heat lost by gas in the other chamber. For this, we will assume a final temperature as T final, which lies between T1 and T2. So the heat gained can be written as Nc into delta T, and the heat lost can be written as N dashed C into delta T. C will be same as it's the same gas on both sides. Now the number of moles in the left container N can be written as P1 V1 by R T1. Delta T is final temperature minus the initial temperature, so it is T final minus T1. And this is heat gain, so delta T is the amount of change. We have to write the positive value, according to assumption at least, we have to write the positive value for delta T, which is T final minus T initial. Now N dashed is P2 V2 by RT2. and delta T will be T2 minus T final in this case, as T2 is a higher temperature. So that should be it. In this equation, the only unknown here is Tf, so you can use this equation to get the final value of temperature. The next question is question number 14. There's a gas which has a given value of Cv, behaving ideally, was allowed to expand reversibly and diabatically. It's a reversible process. Okay. From 1 liters to 32 liters if the initial temperature was 327 degrees Celsius. The molar change in enthalpy. Okay, because it's an ideal gas, the molar change in enthalpy delta H can be written as N Cp delta T. Number of moles. Okay, it's molar change in enthalpy, so number of moles is 1. This is known. Cp is known because Cv is given as 5 by 2R. So we need to find out delta T. We need to find out T2 minus T1. Now T1 is already 327 degrees Celsius. So all you need to do is find the final temperature. Okay, so because it's a reversible adiabatic process, you can use the equation Tv to the power gamma minus 1 is constant. So T1 V1 to the power gamma minus 1 should be T2 V2 to the power of gamma minus 1. Now this equation will give you the value of T2. Right. Right, it will give you the value of T2. Everything else is known. So you find out T2 in this, and you use that to find the value of delta T, which can give you delta H. Next question is question 16. Okay, so molar heat capacity for the process. Now molar heat capacity for any process C molar has to be written as Q by N delta T. Now delta T is not known. Okay, so see, we have 100 calories of heat, so Q is given. The work done W is given. So you can write delta U as Q plus W. Now Q is 100 calories, convert that to joules. Now system does 209 joules of work, so W is minus 209. So use Q plus W to calculate delta U. Now once you know delta U, you can also write that as NCV delta T. Now because Cv is known, it's a diatomic ideal gas, so Cv is known. So N into delta T can be found out from this part. Now use N delta T product in this equation to calculate the value for C molar. Okay, question 17 says we have ideal monatomic gas which T is Kv. Now since T is Kv, this is an isobaric process. And it says find out the molar heat capacity of gas during this process. Now because in isobaric process, the molar heat capacity is simply Cp, which we know to be 5 by 2R for a monatomic gas. Okay, the next question is question 19. Expansion of ideal gas. Mass time it's at constant pressure. Okay, it's at constant pressure. Now V by P is nR by P. Temperature used in this case is obviously the temperature in degrees Celsius. So if you use the temperature in Kelvin, the axis will shift. Anyways, V by T is nR by P. So for a V by T graph, the slope has to be N into R by P. R is a constant, the slope has to be N by P. In the first case, we have a gas of mass M at a pressure P. And in the second case, mass is double, so number of moles is doubled as well, and pressure is doubled as well. Basically, N by P remains constant. N by P remains constant for the two processes, so the graph will be same. This will be B. The last question in this section is question number 20. Just 1 mole of an ideal diatomic gas is taken to a cycle. Okay, it's a P versus V graph, and the average molecular speeds in the states. Okay. The average molecular speeds, average molecular speed V average has the formula 8 RT by pi m, square root of that rather. So we can just write V average as proportional to root over of t, which is also true for any other velocity, any other distribution velocity. Now, since V average is proportional to root over of t, you just have to find out the temperature in each of these cases, which is, I think it's given straightforward, it's directly given. Now, in the first case, we have PV as P naught into V naught. In the second case, PV has become 4 times, and in the third case also, PV is 4 times. And temperature is proportional to that. So V1 is to V2 is to V3 will be proportional to P naught is to root over of 4 P naught V naught is to root over of 4 P naught V naught. So it's 1 is to 2 is to 2. Okay, that's it for this video.